Hello, good morning, everyone. So in this session, we talk about other things that you can do with CompuCell, and we talk about how to use intercellular forces or intracellular forces with spring links between cells and compartments. We're gonna work with a basic example, and then at the end, we'll be trying to make a model of convergent extension of tissues using the force that the cells can exert on one another. Okay, and this use of links will be more explored in the next session hosted by Prion, where she will show how to use them with cell compartments, and when you have both, then you can really do very nice stuff with the cells. Okay, so I again, this session is being live recorded and streamed to YouTube, and the recording will be distributed. Feel free to use the buttons, go slower, go faster. If you have questions or any kind of issues during the exercise, please reach out to us in the chat. If I cannot answer right away uh, during the lecture, someone can meet one-on-one with you on the breakout room sessions. Okay. Uh, Okay, so I like to start this module by just showing this video. So this zebrafish embryo live image for many hours, and you can see the cells. And I just want you to look and kind of figure out what's going on at each time point. Okay. So if you want me, I can play it again. What's going on? The cells are undergoing a Peabody. They are just covering the yolk of the cell. The cells are growing. They are dividing, but they also has a lot of cell movements and cell rearrangements. Okay, right now they are converging towards the center, and then they start to form other structures. There you can see the notochord forming. The cells here next to notochord are epithelializing. Then you can see the formation of the somites sequentially from the anterior to posterior direction, and you see there are a lot of things going on. Okay, uh, and the cells are not just sending signals on and off, and they're not just differentiating. Okay, if you go to pure biologic talks, you may see it seems that the only thing that cells do is change their genes and uh, maybe read and spit out molecules. Here is very clear. I believe that the cells are exerting forces on one another. Otherwise, you cannot get those kind of shapes. You cannot get those morphogenetic movements. Okay, and with and then the question is okay, how can we get this in our model? Okay, we can see that the cells must be exerting force one another, and with our CompuCell simulation, we can actually add a little bit of that. Okay, but today I'll be showing how you can actually add those forces in a more explicit way, where the cells actually directly engage with their next neighbor and start to pull them together, or maybe even push them away, if that makes sense in your particular situation. Okay, so and this has been done a lot in our previous CompuCell simulations. So James had already shown this movie of retinal neovascularization. You have a lot of things going on here between the cells, but one thing that is happening is that the cells not only have passive adhesions with the neighbors, they also have a more strong adhesion through intercellular junctions, and this is modeled by adding links between those cells, so they actually they are a little bit more resistant to disruptions from other tissues. Okay, here is the example that I promise that you end up doing today. So we have the initial epithelial layer that we set up at the very end of the last module, module 4.2 yesterday. And here what's going on is that those red compartments, which the apical side, they have a spring force between them and a subset of them right in the middle. The spring force becomes stronger, and then they lead to the uh, kind of conversion of those cells right here and the formation of a furrow. Okay, so that's the beginning of invagination process. And here on the top bottom, you see a process of uh, mesenchymal to epithelial transition, where the cells were initially have no compartments and then they have compartments suddenly. And two things happen with the compartmentalized cells. First is that they start to elongate along the apical and basal direction, and also they exert force one another that leads to the apical constriction of the cells and then the formation of these epithelial balls. Okay, and in this particular example, this was used to model the formation of ectopics without a clock and waveform mechanism. Okay, so today we'll be learning how to actually add those little white things between the subcompartments, which are the links. That's how you visualize the links in the CompuCell3D player. Okay, so this is the plan for today. I will start with a brief overview of how links work in CompuCell3D. I'll do some simple exercises to illustrate how to add links and how to manipulate them. And then we'll end up by creating a simple model of conversion extension in CompuCell3D. Okay. So, links between cells or spring force between cells are implemented in CompuCell3D by using what's called the FPP links, or the focal point plasticity. Focal point is because you create a constraint between two specific points in your simulation, and in this case those two specific points are the center of mass of a cell and the center of mass of the neighboring cell. Okay, so this focal point plasticity link imposes a new Hamiltonian term or new energetic term in the total cost function of your simulation, and it basically follows the same kind of shape form as the other constraints. You basically have a parameter that regulates the strength of the constraint, the lambda, and then you have a difference between a current value and a target value square. Okay, so here the target value is going to be the ideal distance between the center of mass of this cell and this cell here on the left. Okay, so that would be the ideal distance, and the little d here is the distance between those two, the actual distance between those two cells. Okay, so what the system wants to do is to preserve is to keep those two cells at this ideal distance between themselves. Okay, so every spin flip that this cell has or this cell has undergoes, you change the center of mass slightly, and that change can be either towards, by decreasing the, can either decrease or increase the distance between the cells, and that can either be towards the ideal distance between them or away from the ideal distance between them. Okay. So there I ask, can that be used for floating anchors? Like we talked before, yes, it can be used. If there's time by the end of the session, I would like to just try to make a live modeling session in front of you and try to do an example of a cell throwing anchors in front of it and using that to move. Okay, so the distance has to be distance between 2 points. The most common applications that is to associate those 2 points to the center of mass of the cells. Okay, but another application is to have one of the anchors, one of those points to be the center of mass of the cell, and the other point to be a fixed point in the space. So an anchor to the substrate or some kind of other biological region that's not being explicitly modeled in your simulation. Okay. So again, what that means? So these sigmas here is the ID of this cell, and the sigma prime is going to be the ID of the second cell, right? So this identifies the cells, and this D as a function of the sigma is going to be the distance between the center of mass of this one and the center of mass of that one. Okay. Uh, so as specified here, and this is going to be the strength of the interaction. Bigger lambda will be a stronger uh, constraint, and a smaller lambda going to be a weaker constraint. So you can always regulate the the contribution of this type of interactions by choosing the appropriate value of the strain of the constraint with respect to the other constraints that you have in your simulation. Uh, is there any questions about this so far? Is this clear? Okay, so how you add those focal point plasticity plugins, or FPP, we like to call it FPP for brevity. So when you create your simulation and you know that you want to use them, you have to select focal point plasticity in the cell properties and behaviors panel in the wizard when you start your simulation. So when you select that, it will automatically generate all the possible. It will make a template of all the possible links between all the cell pairs that you have in your simulation. Okay. And it's always a good idea when you're using focal point plasticity to always check the cell neighbors, okay, option in the wizard panel, because you want to usually get a cell and go over its neighbors to check uh, who, if you want to create a link from the Python level, you probably want to also have the ability to track to know which cells are neighbor of whom during the simulation. Okay. So when you start simulation and you set to the CompuCell3D wizard, I want to use links in my cells, it automatically pastes the base code for you in the XML, and it comes with its own syntax, right? So if you do a simulation right now with 3D focal point plasticity, you see that the wizard generate this code for you, and we're gonna go over how this code, what's the meaning of all these uh, terms here. So the plugin is named focal point plasticity, right? And you have many sets of parameters for each pairwise cell interaction. Okay, so in the simulation where you have just one cell type, you generate just one parameter. It's going to be between that cell and the second cell of that same type. If you have more than one cell, you have cell A and cell B, then you're gonna generate these 3 times for the interaction between A and B, and B and B. Okay, so for simplicity, let's just look at this where it generates links between cells of the same type. Okay, so lambda here, the first option, is just the strength of the interaction. Okay, so usually comes with the value of 10, is the same as the temperature of your simulation. Okay, and the other one is the target distance between the cells, so the ideal distance between the center of masses of those two cells, which usually starts at the value of 7, which is the width of your cell. Okay, so this and this, I guess it all makes sense. Okay, but you can see that you have also other parameters besides those two that explicitly appear in the Hamiltonian. So the first thing I have noticed that this will be repeated for different cell pairs. You also have this maximum distance. So this is used as a criteria of when to break the link. So if you have two cells, right, two other interactions with the rest of your simulation object, those two cells can actually be driven apart, okay, from other forces, and at some point this link should break. Okay, you should not keep the cells start to not touch anymore, and it's getting far away more. You should break the link at some point, and this maximum distance parameter tells the CompuCell player when this link should be cut, should not be active anymore. So in this case, if the distance between those two cells exceeds 20 pixels, okay, then you just break the link, okay, and you can make this distance to be whatever value you wish, okay. If you want to have the links to be forming and being deleted in a very dynamic manner, you want to make this maximum distance very close to the target distance, for example. Okay. So the other thing that you can have, you can specify how many links the cell has with other cells of that kind of type. So this is specified by the maximum number of junctions, okay? And here, what you're telling is that you can only have one link of those two. For each cell can only has one link with that same type of cell, okay? So the interaction between my cell and my cell can only have one link. You have also another parameter which will be my cell and cell B. That interaction can have 2 or 3 links. Okay, so in that case, my cell can only have one link at most, even if it's surrounded by 6 cells. But if it's surrounded by cells of type B, right, then if you set the maximum number of links to 3, then that cell can also have 3 links of this towards this different cell type. Does this make sense? Do you guys have any question? Good question from Norma. Is it possible this junction has a direction? The way that you implement this code, it does not have a preferential direction. You're gonna just make a link with the first cell it interacts, okay? Of course, if the cell has only another cell to the right of it and nothing around, then it will only make a link with that cell, so we have a direction. But you cannot. If the cell is completely surrounded by other cells, you're gonna make the link with whatever cell it interacts with. If your question was about if the link itself has a directionality, right? Then the answer is no, because the link is supposed to be the same for the cell A and cell B. If they have a link between themselves, they both feel the same force with the same. It basically is obeying Newton's third law, right? So if cell is having a force with cell B has the same force with cell A, but in a different direction, right? Yeah, but you can actually play and manipulate the links at the Python level to explicitly say that this cell now going to make with a link with this cell here, and then implement that. Or you can also, at the Python level, delete links based on whatever criteria you like to do. And that's something that you'll be doing for the Convergent extension example at the end of this module. When you initialize, you also have internal parameters. Is this for compartments? Yes, it is. So here, just for simplicity, I just showed the external links between cells of different clusters, but it also has the internal parameters tag for already anticipating a case where you may have links between cell compartments within a cluster. Okay. Are there more questions? Okay, so you see that there's also other options here. You have something called activation energy and also a neighboring order on the bottom. So this activation energy is used to actually facilitate the creation of the links. Okay, so initially when you create your simulation, the cells are there and they do not have the links to begin with, right? So the cell have to create a link, right? Or the player will create a link based on the as soon as a cell interacts with the other cell, or in other words, as soon as there is a spin flip that affects this cell with a neighboring cell, you check if you want to create a link between those two cells. Okay, so if the cell with the other cell type has not already exceeded its maximum number of junctions, they may create a link. However, when you create a link, what happens? You are suddenly adding an energy term to the interaction of your cell. Okay. So if there's a pixel copy between one cell and the next cell, they're interacting, and then you check whatever you want to create a link or not. Okay. Uh, but when you create that link, you're suddenly adding this new energy constraint to your cell, meaning that when you create a link, the energy of your cell just went up by this factor. Okay, so that creation of that link is actually something that is should not be done, because you are just suddenly creating adding a lot of energy to your cell. Okay, so what this term does is lowering the energy of for the creation of the link to make it more likely that you actually will create a link between those two cells. Okay, so this is facilitating the creation the of the link. So usually you set the activation energy to be a very negative number to drive the energy down, but that is only used for the creation of links. Okay, if you make this activation energy to be a very high positive number, like 500, then the links will never be created. Okay, so that's what this activation energy means. So usually you set to minus 50 and you don't think about it anymore. Okay, this neighboring order is determines how far two cell membranes must be during the pixel copy or the boundary movement before you actually check if you want to create the link between those two cells uh, uh, happen. So usually you set a neighbor order of 1. The cells actually have to physically touch each other to create a link. Okay. So there's a question. Before breaking away, can we see oscillations? Good question. Usually not, because this is an overdamped system. Okay. But if you want to have a situation that the cells actually are oscillating with one another, well, you can actually manipulate the target distance between two cells at the Python level to make it decrease and increase over time. Usually, if you have interactions of the links and other uh, constraints in your system, you may have seen sometimes the cells appear, go back and forth, but that's more to the stochastic nature of the simulation than due to some kind of real oscillatory behavior. Okay. Can activation energy be used to alter the balance between adhesion versus contact-based interaction? Yes, you can do that. You can make the cells from the contact level not like to be closer together, and from the link level to actually force them to be close together, or vice versa. So you can adding this new way to model cell interactions actually allows to do this kind of model this kind of situations. Does breaking the link also change the system energy, like reverse activation energy? That's a good question. Yes, it does, but the the short answer is yes, but you do not. That's not the criteria that you use to break the link, right? When you have the two links between the cells, the link will stay there no matter what. When you do a pixel copy or a boundary movement, that changes the center of mass of the cell, and therefore it's linked directly with all the other links. You only take into account the change in the energy that the link uh, energy would have. You do not you do not try to see would my energy goes down if I break the link, right? because the answer will be always yes. So once you create the link stays there forever. And the only criteria that you use to break the link is when it actually exceeds the maximum distance. That's when you break the link. Okay. So if it exceeds your maximum distance, so your distance was 19.9, and after the pixel copy, this distance becomes 20.01, then you break the link. Okay. So it's more sudden change in the number of links. Would you learn towards using links to represent ECM adhesion over low contact energy? Uh, well, personally, I'll say yes, because the contact energy is an energy based on the contact area. So if you have a cell that's sitting on a ECM, if you just slide them like this or that, it's not changing its contact energy, right? But if you have links of the cell center to specific points on the underlying membrane, then doing this, you actually are stretching the links that you had before. So maybe using links from the cell to the ECM, like using this plugin, it may be a better way. And there was a question about that on the very first day of the workshop about uh, exactly about this.
I was wondering if you can define the distance between your cell type, which is on the top, and ECM separately for every cell in the cell type. Is that possible? Like the target distance,
Yes, even have it sell different.
if you get my question.
Yes, you can do. You can so at the XML level, you're gonna make the same distance between every pairwise interaction. So the links between A and B can have this distance. The links between B and B can have a different distance and different lambda.
Yeah,
Uh, but at the Python level, you can actually optimize and personalize, and then each cell, even if they are the same type, can have different target distance,
exactly.
different
That
droplets.
probably
Yes,
that's
you
what
can.
you'll have to do in this case, the ECM and
Yeah,
the cells over it,
yes, you can. Yeah, at
because
the Python
you
level,
have
you can do whatever.
distance which are at different angles to the ECM, right? Okay,
Yes,
great, great. Thank you.
yes, you can do it. Okay, so let's actually start to do the exercise. How about that? Okay, so please on your desktop or um, Nano Hub, okay, open to it, and let's create a new CompuCell3D project. Okay, so I'll give a few seconds to do this. Okay, so CompuCell3D project, new CompuCell3D project. Norma, the answer is yes, you can do that. So now let's call our new exercise as module 4 underscore 1 underscore examples. Okay, and select Python plus XML. Then the system simulations will be, you can leave everything as it is. Okay, you have to add at least one cell type to your uh, model, so you can give whatever name you want. Again, mesoderm, ectoderm, uh, enoderm, or you can just give it my cell as I'm doing here. Okay, hit make sure that your cell type appears there and hit OK. No chemical fields, ignore that. And on the uh, cell properties and behaviors window, you have to select contact, focal point plasticity, volume flex, and that's basically it. Okay. Okay. So make sure you have this. All right. And once you have this, let's complete simulation. Okay. So make sure you have contact, volume flex, and focal point plasticity. On the previous one, this is the most important one. Okay. Well, you usually want yourself to have contact, volume, and FPP. Okay. Hit OK, and then you should have your simulation tweeted. Just click open in player and tell me what you see. Suppose I have to give different energies for different type of links, how to assign activation energy. This can be done on the Python level. Yes, you can do that. You cannot add more than one link between cell pair. That's the only constraint you have. Okay. Um, Unfortunately, add two links between the same cell pair is not possible to do. Okay, so have you guys get to create the exercise? So if you have done, you should see something that looks like my picture on the right here. Okay, you see a lot of cells, and you see some kind of white connections between what seems to be random cell pairs. Okay, if you're not seeing these white links between the cell center of masses, you have to make sure that the visualization of the FPP links is actually turned on. And you can do that by going to the menu, visualization, and make sure you have FPP links with a check mark on it. Okay. Once you do this, then you should be able to see the links. The links are always white, so actually you can select what the link color is. I usually like to make my cells a little bit darker, like this dark green I have here, and make the FP link to be white. Okay, but you can choose that uh, however you want. If I have my FPP links white, then I also like to make my cell border colors to be black, so then I can visualize it better. Okay. So did everyone got here? Let me just throw a poll. Good question. Why is that some cells don't have links? Uh, for example, if you just look at this cell here, okay, can you see my mouse, Sarana? I'm not sure I pronounced your name correctly. Uh, yes. So you see that this cell here already has a link. This cell already has a link. This cell already has a link. This one already has a link. This one already has a link, and this one already has a link. So all its neighbor pick up a pair before this cell actually interact with them. So what happens is, and because you have a maximum number of junctions set to 1, okay, uh, this lonely cell here end up without a pair, okay. So that is a situation that can happen. Does it make sense? Okay. So you may have a situation that some of your cells become frustrated because they cannot pair because the other cells already have a pair. So we are not. So in this case, you are only letting one pair, one link per cell. Okay. But that actually is a good question because that's what you want to change next, right? Uh, so what's going on here? Okay, we are only allow one pair of cell because the maximum number is set to 1. And exactly as you said, some cells may be left single, right? So let's just now do this as an exercise and change this parameter to 2, 3, and higher, and tell me what effects you see. Okay. So I'll give you a few seconds to try to do this. You should be very quick. So I just throw up a poll again to see how we are doing with the exercise. So I just want to run simulation again and just change this number, the maximum number of junctions from 1 to 2, 3, 4, and keep increasing. Okay. So if you make the to 2, you should already get rid of most single lonely cells. Can I just quickly see the wizard steps again? Yes. Let me go back. So, well, I guess this up here is no problem. Python plus XML. This simulation wizard is, there's nothing you need to do here. Uh, you just add one cell type, okay? You ignore the chemical fields. And here you have to select contact, volume, okay? You need to select the volume, otherwise the cells will disappear. And you usually want to select contact, otherwise the cells may just squeeze one another and start to fragment. So you need those two, and you definitely need the focal point plasticity link plugin. Okay, and that's everything that we did to set up simulation. Okay. And in the code itself, you have actually two FP links parameters, one call parameters and the other call internal parameters. The internal parameters is only the case when you have clusters and compartments. So if you do changes, you have to only do that to the parameters part. The internal parameters option that gives you can delete and or ignore for the moment. Okay. So seeing that most of you end up the exercise, so let me proceed, and this is more or less what you should be seeing. As you increase the number of junctions, you start to get well, the systems become more connected, right? And I guess at probably when you go to 3, the system is percolated in terms of ring. All the cells are eventually connected to some uh, to all the other cells in the simulation. Okay, and of course, once you get past 5 or 6, there's no way you can create more links, because in a two-dimensional lattice, in a two-dimensional simulation where the cells are all the same size, they tend to rearrange on a hexagonal, on a honeybee pattern, and then all the cells have at most 6 neighbors. By chance, they may have 7, but usually that's what happens. Can the links determine the final set of structure? Yes, it can. And that will be the very next exercise that you'll do. Okay. So this is, we just are playing with the number of links of the cells. What you can also do now, you can change the uh, target distance between the cells. Okay. Uh, so in the next exercise, I would like you to choose a connectivity of 3 or 4, maximum number of links per cell. 3 will be actually a very good number for you to do the next exercise. Set the maximum number of junctions to 3 and play with the maximum distance between the cells. Okay, make it smaller than 7 and then start to make it bigger than 7 and tell me what you see. How do I access the toolbar to select visualize FPP? Okay, let me go back here. It's the menu, visualization, FPP links. Okay, if you want to change the colors, you can just click this button here, the tools, and then that will allow, and then if you go to the cell colors tab, it allows to select the colors of the cells and also the boundaries and the FPP links colors. Okay. I'm gonna relaunch the put, see how everybody's doing. So I want to set the maximum number of junctions to 3 and play with the target distance between the cells. Okay, make it smaller and then make it longer. Okay, most of you are finished with the exercise. Yes, please, if you have any issues with Nano Help doing this exercise, let us know. Don't get stuck. We can help you. We have lots of people here besides me that can help you, and we can work with you on the breakout room. Okay? All right, so many people have already done the exercise. So this is something that you should be seeing, okay? So here I'm setting a maximum returns of 3 or 4, okay? 3 will be nicer, actually. So if I decrease the distance from 7 to a lower value, I'm kind of, all the cells want to actually be a little bit closer than you normally do. So we actually increasing the whole tissue becomes more stiff and more tense, okay? But if I make the target distance higher, uh, then the cells actually start to pulling one another, okay, away. So if I do this, the tissue becomes a little bit rougher because the cells interact and they just are kicking themselves and moving a distance further away than what they would normally do by the interaction distance, okay? So, and if you keep pushing the target distance to even higher values, you get what you see here on the right panel, where you can actually drive the tissue to fragment in a spectacular way, as you see there, which I'm not sure if there's any real physical biological application where this happens, but you can, by manipulating this the links, you can get this kind of stuff. Daria. So if I make the target distance negative, it's like a contraction force. Yes, it will be a constraint that will never be. Let me see. Yeah, you'll never able to get the to that condition. If you just make the target length to be 0, it will be a contraction force, right? You can use that to if your model is visualize the apical side of the cells and they are undergoing apical constriction, right? So if you're seeing some kind of invagination event from the top, right? Make have the cells have links and make the target distance to be 0 in a subset of cells. That to make the cells shrink, and that will be like seeing a invagination event from the top. Okay. I'm not sure if making the target distance negative makes any sense, but making the target distance lower than the typical than the radius of the two cells that are interacting will lead to some kind of contraction. Yes. Every time you have a boundary movement, that will be affecting that energy term, and some of those pixel copies will drive the cells toward the target distance, and some will drive it away. And you're using these links to actually set up what should be the ideal distance between those two cells. Okay. So let's now try to do some other exercise. Okay, now you have to go to 3D and create a new simulation. And here's a little bit more complex. I want you to do a simulation with actually two cell types. Call one G and the other P. So, and you can choose the colors to be green and purple. Okay. And I want you to kill the links between those two cell types. And I want to try to Uh, just make a simulation with two cell types, right? Like this. And let's try to use the links to actually make the try to do some kind of cell type mixing between them. Okay. So the exercise 4.4.2 now is let's create a new simulation with focal point plasticity, and the simulation will have two cell types, okay? And I want you to manipulate the link parameters to either induce cell type mixing and to induce cell sorting, okay? So actually the initial simulation is just let's try to reproduce what I have here on the top right. Make uh, only the purple cells have links and only the green cells have links, and see if you can get something that looks like this. Okay, you can in order to do this you have to set the maximum number of junctions between green and purple to 0, so those links will not be created, and tell me if you can get something that looks like what I have on the right. Okay. So question, what exactly are the internal parameters used for? That's for the case when you have cell compartments. Okay. So when you want to add links for the compartments within the cell, within a cluster, then instead of using the parameters, you'll be using the internal parameters. Okay. That's not the case in this session. In this module, you'll be only using the external parameters. So all the internal parameters options that you get, you can just ignore them. You can even select all of them and delete. Okay. The next session from Prion is it will be about how you can use links when you are modeling cells with compartments. Volume flex. Normally you select volume flex. Sorry. So I can go back here. You'll basically will be following the same steps here in the slides. And by the way, those slides had already been uploaded to the student materials. Okay, should be module 4.4. You have all those slides there for you. You'll basically be following the same steps here, a name for the exercise. You can leave this part exactly as it is. The only difference that here you'll be adding two cell types, and I suggest name them G and P as stand for green and purple cells. Okay. Then you proceed as always, and then you do contact, volume flex, and focal point plasticity, and the 3D should add the code for you. The difference now that you have, instead of have just one focal point plasticity parameter, you have three. You have between G and G, G and P and P. Okay. I think Hayden just add the link to the today's slides. Uh, Links are created. Well, initially it doesn't have no links. Okay, so at the very start there's no links between the cells. As soon as they start interacting by a boundary movement between them, two cells, right, or a pixel copy involving two cells, then you create the link. So you can see
Right.
that
So,
the
so my question is that let's say a link breaks, is that
yes,
cell allowed to make another link?
yes, it
And
is. Then it's
okay,
free to make
cool.
another
In the
link.
proceeding. So it establishes over time basically. They can
Yes,
form new links. Cool. Thank
exactly.
you.
Yes. Thank you for the question. So what I here I'm asking to do three things, right? First is try to reproduce this picture on the right, where only the purple cell has links and only the green cells have links, and try to make one shorter, one a little bit bigger, and see what the effect is. Once you're done that, you can proceed to try these other two challenges here, which is induced cell mixing or induced cell sorting. So for the very first part of the exercise, how are you guys doing? I'll send out a poll to just check. Okay, can someone help Megan in a breakout room?
Yes, yes, let's go. Uh, Pedro breakout room.
Okay, thank you, Pedro. Okay, since that's most of you got this very first part of exercise, once you got that, please now go back to your code and change it to try to induce cell mixing. Okay, how can you use links to induce mixing of cells of different types? So the aim here is to try to get some kind of checkerboard pattern in your simulation. So one thing that you guys can do, which was done on the previous on last year's workshop, is that once people start getting results, they take a screenshot and paste it on the Slack channel for everyone to see, uh, and that's fun because then I can actually see what you guys are getting in your computers. So feel free to do that if you want to. So let me send a new put, see how you guys are getting with the cell mixing example? So how many of you got the cells to mix? Okay. So at least 6 of you got the cells to mix. What you guys did to get it working? So in the interest of time, I will just okay. I know that few of you still need more time to induce the cells to mix. What I will do now is just have this slide here to see what has been done to what did I do to get those two different kind of behaviors. Okay. Uh, so to induce cell mixing, what I did is the following. I set the maximum number of neighbors between green and purple to 0, so they will never form heterotypic links. Okay, and then what I did, I set the maximum number of neighbors between green and purple to be 3. Okay, and then I left all the other parameters to be as it is. Okay, so when you set your parameters to something that looks like this, what's going on? Only the heterotypic cell types create links. Okay, so now you only have links between green cells and purple cells. Okay, and then what happens that when the cell has this kind of neighborhood, they like to stay in that because you have the link between those cells. So usually the cell random movements will make you do some kind of diffusive movement of the cells within the tissue. Okay, but once you have those links set up, those links and because it only breaks at a very high distance, then they stay there. Okay. So when you choose this set of parameters, you start to do some mixing. And one thing that I did, I set the target distance between the links to be very small, 1, so the cells have green and purple start interacting with the links. They really want to pull on those two together, right? They cannot actually get they can never reach the target distance of 1 pixel because the cells have volume. So there's some kind of volume exclusion going on. But I set the maximum distance to be 7, which is typically the normal distance between the cells. So this means that eventually the cell will fluctuate and break the link, which allows for the cell to make a new link with a different cell type. So if you make the target distance to be about the diameter of the cell, you allow a frequent remodeling of the link to happen. Then the links become very dynamic. If you make the maximum distance to be 3 times the diameter of the cell or something like that, then the link will never break. So this is one thing that you can do. You can make the target distance, the maximum distance, to be very close to the target distance. Okay, and then the links form and break all the time. So the other exercise, the cell sorting, this is how I model it. In this one, because I don't want it, I want cell to sort out. Okay, I did the reverse. I set the maximum number of neighbors between green and purple cells to 0. Okay, so they will not form heterotypic links, and you only form homotypic links. Okay, so I only have links between purple and green cells. And one thing that I did, I made those green cells to allow those green cells to create more links than the purple cells, and I make the string between the green cells to be between the green, the strength of the link between the green cells to be stronger than the purple cells. Okay, and with this kind of choice of parameters, I can induce cell mixing, as you see here on the top right. So you can try other values to see what happens, but this is a set of parameters that I can guarantee that you give this kind of results. Okay. So is there any questions? How are you guys doing with the exercise? I'll relaunch the pool here. Okay. So I've let you try it for yourself in the beginning, and now I'm just showing my my set of parameters. Okay, can anyone help Sonia in a breakout room?
Yeah, you should be able to join Pedro's.
Okay.
Hi, Julio. I have a doubt.
Yes.
So in the left case where you're trying to have mixing,
Yes.
if you have like a cell which is, let's say, a green cell and it's surrounded by just green cells, then it's never gonna mix, right?
Yes.
So that's what I'm getting, and I'm wondering how are you able to get to this? Did you start with the initial layout which had some separations between cells or something? Or
Yeah, just by chance, you may have this kind of situation where one region of your simulation just happens to be populated with green cells, and
yeah,
cells at the middle just never sort. Okay,
right.
so if you wait enough time, the cell, because the cells are always moving with pixel flips, right? Pixel copies. Eventually, that cell will see a purple cell.
Okay, cool. And make a link.
But one thing that you can do to make sure that to favor this link remodeling to be very often is by if you set the maximum distance between green and purple cells to be to 7, which is very close to the diameter of those cells. Okay,
Uh-huh.
then those links will be forming and breaking all the time.
Yeah.
That should help to for the cells to be more dynamic and more that will allow more movement of the cells. The system will not be freeze on the first set of links that they create, and then you eventually get the mixing to be well
Yeah,
behaved.
makes sense. Yeah, cool.
Thank you for the question. Are there more questions or comments? I think most of you, well, according to the pool, actually completed the exercise. You don't need to complete all the exercise right now. If you just got the first one and one of these to work, that already very good. The idea is how you can manipulate links by just setting up the parameters at the XML code, XML level. Okay, so but this, of course, once you set up those parameters, you cannot change them in the multi simulation. So you may have, suppose you want to create a simulation that the first the cells mix, and then I don't know, you add some kind of treatment to your culture, and then the cells, one of those cells differentiate, and now they want to sort out from themselves. Okay, so you cannot do from the XML level. That's a change that you have to do on the Python level. Okay. So the question that I will cover is how can you change the FTP links at the Python level. Okay, so the first thing you have to do, you have to, in the XML, you have to uncomment the tag which says local. Okay, so this local tag here, when you have that turned on, that means that the parameters of your links can actually be changed and optimized, and they can have different values. You can change them on the Python separables. Okay, so if you have, so for the if you do the add the local tag here, you just have to uncomment them. Then this allows to do change on the separables. When you are manipulating links at the Python level, you want to leave the XML as it is, but you may want to set the maximum number of junctions of all the cell parent tracks to be 0. And in this case, the player will never make a link for you. All the links that appear in your simulation will be the ones that you told the player to create at the Python level. Okay, so that's basically what's saying in the slide here. Once you turn on the local tag in the XML, you're able from the Python level to create new links, update existing links, change the parameters, make this link stronger or weaker, change the target distance between the links to be bigger or smaller. You can delete links, and you can also retrieve information about the links. Okay, so this is done with CompuCell3D Python, focal point plasticity, and you just click there. You see that a lot of options to create links. So we have some that is just to get information about the links. This is just to create links, delete links, right? And you can also do loops. You have a cell and then you want to interact with all the other cell neighbors that have links with the cells. You can do loops over the cell of the neighbors of the cell that are connected with links. Okay, so you have all these options, so which illustrates all the things that you can do dynamically with the links within the at the Python level. Okay, so the ones that you in the next exercise you'll be only be using 2 of those options, which is going to be link management, create FPP link. Okay, when you select that, what you get is you get this you get this new line in your Python level. You have link equals self new FPP link. So this is going to be the first cell that you have the link. The second here going to be the initiator, be the second cell that you create the link. So there could be your cell and your neighbor, or cell 1 and cell 2. And then you have these other options here going to be, you set the lambda distance, okay, or lambda link, which is going to be the lambda parameter. Target distance going to be the ideal distance between the center of mass between those 2 cells, and the maximum distance will be the distance at which it breaks. Okay, so at the Python level, you just select this and you paste the code, and that's the code that actually create the link between 2 cells. Okay, the other thing that you want to do, you want to use the delete FPP links option, and if you select that, you just paste a code called self.remove all cell FPP links, and this you drag a cell, pick up a cell, and you're gonna just delete all the links that the cell has with all the other cell types. Okay, so so with this now we can, using the link management at the Python level, we can actually create a model of convergent extension of tissues. Okay, so and that's going to be the final exercise for today's module. So let me give a very for those who do not know what convergent extension means, is a very basic mechanism of tissue morphogenesis. Okay, so in this very brief and oversimplified recap of development, our organs, they start usually as a single cell and start to divide. Okay, and if you just have cell division, the best thing that you can have is a spherical tissue. Okay, that's what you get if you only have cell division proliferation. So at some point in development of either a mouse, a zebrafish, or even us, you have to break the symmetry and stabilize an anterior posterior direction, an axis. Okay, And once you break that symmetry, you usually want to actually have the tissue to elongate along this axis, right? The organ is to elongate. And that's usually done through the convergent extension movement, where the cells actually start to move in a certain direction or towards an axis. And because they want to move along this axis, the whole tissue starts to extend in the opposite direction. So the cells are here and they start to interdigitate, and as they do this movement, they converge on this axis and extend in the perpendicular axis. Okay, so that's called convergent extension of tissues. Okay, there are two ways that cells can achieve convergent extension. One is by having cells remodeling the junctions and undergoing what's called T1 transitions, and that's usually what happens in highly epithelialized tissues, like in the Drosophila germ band extension. Okay, as you see here on the right. But that involves remodeling of the membrane. So you usually have a membrane that becomes very rich in actin motors and actin filament, myosin motors and actin filament, and then that contracts the tissue. You get this four-way vertex forming, and then the tissue relaxes by creating another boundary in the perpendicular direction. So if many cells do this, that leads to the convergent extension of the tissues in this manner. Okay, but another way that you can achieve convergent extension is by just have the cells moving or crawling on top of each other along a specific direction, and that actually was the way that this kind of cell movement was first characterized by the work of Ray Keller and the members of his lab. Is that the cells, when you have a highly mesenchymal tissue, the cells are initially polarized in one direction, and then they become polarized in a certain direction, and then they start to pull one another along a preferential axis. That leads to the cell interdigitate, okay, in a specific direction, and elongate in the other. So this is the model that you can actually implement using FPP links in our models. Okay. You did your PhD in Ray's lab, so you know exactly what I'm talking about, right? Yes. Okay. So what I want to do in the next exercise, I want you guys actually to go to Tweedit and create a simple model of convergent extension of tissues. Okay. So I want you guys to create a simulation. All the cells will be of the same type. You can call them, I don't know, whatever, mesenchyme or micelles or whatever. Okay. So I want to create cells that have volume, contact, FP links, and cell neighbors. So just do a simulation as before, okay? And I want to, at the Python level, do the following. At every given set of Monte Carlo steps, I want to go over autocells, delete all FPP links that they may have, okay? And create new ones, okay? But the creation of FP links must follow this set of rules. The links must be between neighbor cells, okay? And the neighbors must be either to the left or to the right of the cell, okay? So in order for this to work, once you create your basic simulation tab, I want to set all the maximum number of junctions to be 0. So you are only be creating the links at the Python level, okay? And I want to uncomment the local tag so that allows to create and delete links from the Python level, okay? And for the creation of links, you may want to use, as you go over the cell neighbors, you want to use this command here to get the vector between those two cells, and you can use the import the map function and use the a tan2 yx that returns the angle between those two cells. So this returns a number between pi, minus pi and pi, and from this you can decide whether your neighbor cell is to the right or to the left of your cell. So this is a more advanced exercise. It's still a very simple model, convergent extension use FP links, but that would be the final exercise to do. So this is a little bit of a challenge, but let's see how you guys do it. Are there any questions or comments? You can feel free to ask.
Will we need the neighborhood tracker plugin for this?
Can you repeat?
Will we need the neighborhood tracker plugin for this in the
Yes.
XML?
Yes. So in the initial one, you have to select cell neighbors because you have to go over the neighborhood to
Yeah.
list out the neighbors of the cell to. Yes.
So we should add it additionally in the XML, right?
Yes. Well, in the wizard, you can select that. So.
Okay, I think I forgot, but yeah, I'll check it. Thank you.
So, yeah, you can still retrieve it by if you go to.
The code snippets let you add it very easily. Just go to the CC3DML pull down menu.
Yeah, in the
And just the key thing is make sure that when you paste it in, you don't paste it in the middle of another
plugin.
plugin definition.
Yeah.
Because
Yes,
that will
yes.
cause CompuCell to crash in an uninformative way. It will just disappear. If they're
Okay.
when people see CompuCell just disappear as opposed to showing an error message, that usually means there is a syntax error or character problem in the XML.
Good, thank you.
Yeah, as Jim says, always a good idea to have the cell neighbors selected all the time because you use them very often. Okay, you always want to inquire who is the neighbor, who is surrounding your cells, and that does not make your simulation any slower. It's very negligible the effect of this on the speed of simulation. So actually, it's better if the computer always start with this cell neighbor selected. So once you get to the Python level, you want to be using the create FPP link and the delete FPP link to implement, to do this exercise. So we have 5 minutes left according to the original schedule. What I think I'm going to do is I'll make a share, a split screen here and try to show the exercise and a code that I'll share with you that actually implements this. Okay. So I'll stop sharing for a moment. And let me ask you, can you see my screen now?
Yes.
Yeah, so here is the exercise, and here on the right is the code that I need to implement this exercise. So when you create it, the module, you have to do the following. I'm going to create, you create a new one, continue, you leave all this as is. Okay, you add the cell type. Okay, add. Okay, ignore the chemical fields, and here you want to select the contact, the focal point plasticity, volume flex, and cell neighbors. Okay, because I want to go over the cells. Then that's basically what you do, and then you should have a kind of cell template that looks as I have here. Okay, I just gave my cell type name type 1. Okay, and then I have center of mass, neighbor tracker, focal point plasticity. And what you want to do in this focal point plasticity is, first you want to ignore the internal parameters. You can just comment them or just leave like that and set it to 0. And the parameters themselves, you also set that to 0, because you don't want the player to create any link for you. You want to create all the links yourself from the Python level. So what you have to do, you have to make sure that you have this local option untagged. Okay, so what's doing, you have the focal point plasticity plugin. Okay, you enable it to modify from the Python level, and you set all the maximum number of chunks to be 0, meaning that the player will not create for you. If it exists, it's only because you created. Okay, now if I go to the steppable files, this is how I created the simulation. Okay, let me just move this a little bit here, make this a little bit bigger. Okay, so are those letters legible, or should I make it bigger? Legible. So what does those neighbors actually do? They track who is neighbor of whom. Okay, so from that tracker, you can actually inquire. You can grab a cell and go over its cell neighbors. That's what it allows you to do. Okay. I'll try to make my text a little bit bigger. So this is how I code it. Okay, so I have a steppable, which I call, well, it's the basic steppable that you have. And what I do is I gonna make a step function. I just define two functions, delete links and create links, and I write those two functions here in my code. So in the steppable, you have usually the start, step, finish, and on-stop functions. You can also create your own functions inside the steppable file. Here I create a function called delete links, which I call here. And what this does is just I go over all the cells in my simulation, okay? And I use the self remove all cell FP links. So what I did here is basically I create a function, and I did here CompuCell3D Python visit all cells. So that pastes the loop over cells for me. And once I have this loop over cells, I set my cursor inside, and what I do, I go to focal point plasticity, and I select the option delete all links attached to a cell. So I select this, and then it just it pastes the code for you. And so that's basically what's going on in this first option here. So the first thing is I delete all the links. I go over all the cells and delete the links. Okay. After I delete the links, I create new links. And this is how I code the creation of the links. Okay. Again, I go over all the cells in my simulation, and then I do the loop over all the cell neighbors. I believe you have already seen how to do this loop. If you don't remember, you just inside the cell loop, you have to go to here to CompuCell3D Python visit all cell neighbors. Okay, and if you click this, it go over all the neighbors of your cell. So when you have the cell neighbor option turned on, it allows you to do this kind of loop over of your cell neighbors. Okay. So why do I create links and delete them again? So first I'm deleting the links, and then I create the links again. So the idea is to have the links dynamic. I want to create the process the following. I'm making connections of the cells to my right and my left, and because I now have those links, I'm gonna pull those cells, and as I'm pulling those cells, your tissue may be remodeling, okay? And I may end up with new neighbors to my left or to my right, okay? So what I want to do next, I want to delete the links and do a new round of pushing my cells from the left and the right based on my new neighborhood after this remodeling, okay? So if I just do that once, if I just put the cells on my left and right, I pull those cells, eventually they'll get close to me, and then nothing more happens because I only have one round of pulling. What I want to have is to have multiple rounds of pulling, so you can keep deform the tissue and eventually get the whole tissue to converge and elongate. Oh, got it. Okay, thanks. Okay, so I first delete all the links. Okay, so at the beginning simulation you have no links, and this delete links will do nothing. And then what I do next is I create the links. So I go over all the cells in my simulation. Then I go for all the neighboring cells of my simulation. Use this command here. So this returns your neighbor and the common surface area between the cell and the neighbor. Okay. And then what this command here on line 33 of my code does is check if your neighbor is actually a cell. Okay, so when you go over the neighbors of a cell, some of these neighbors will be a cells, but if you're on the boundary of the tissue, some of the neighbors might be actually the medium. Okay, and the medium has no properties. So before I do anything, I want to check if my neighbor is a cell or not. And you do this asking, is this neighbor object actually exist, right? Because the medium is an object that has no properties, does not really exist. You just get a 0 there. So this condition here just check if you actually are interacting with a neighbor, okay, with a cell. So if you are actually interacting with a cell, what I do, I use this command here to get the vector between the cell and the neighbor. So let me just move here. This is the whole command. So invariant distance between cells, and then I from my cell and the neighbor. Okay, so I get the XYZ vector components between this cell, my cell center of mass, and the neighbor center of mass. Okay, so how can you get this? You can get this by going here on the CompuCell3D Python, cell attributes, and here what is? Here, CompuCell3D Python, distance vector transformations, and distance vector between cells. If you click here, right, you can get that command that you see on line 34. Okay, so click here, you get X, Y, Z, and then what I'm doing, I'm going from the X, Y, well, the Z is 0, from the X and Y coordinates, vector components, I can actually calculate the angle, and I can use to by just using A10 and give the Y and the X, and then give me the angle from the X direction. Okay, what I'm doing next, I'm convert this angle into degrees because it's easier to work with. And then what I'm doing is I take I'm checking if this angle is within some kind of maximum angle, or to the right or to the left. Okay, so I'm just taking the absolute value of the angle, or the angle minus 180 degrees, and compare to some kind of predefined value of the maximum angle, and is it within this angle to the right or this angle range in the left. I create a link between my cell and the neighbor, and I give the cell the neighbor, okay, and then I give the strength of the link, the target distance, and the maximum distance between those two cells. So you can see that I have a max angle, strength, target, and max distance. These are all parameters that I define here at the beginning of simulation. So in your Python code, you can also define those global parameters. So I get global strength, target distance, maximum angle. Okay, so I define them as global parameters, and here I give their number. So the strength will be 10, target distance will be 0. So they want to pull each one together as close as possible. The maximum distance will be 1,000. So I don't really want to break them automatically. I break them when I delete the links. And I made the maximum to be 45 degrees. So 90 degrees on the side and 90 degrees on the other side. So this is the code for that actually implements convergent extent of tissues here. I'll make that available, but that's basically how you implement it. what I'm doing here is I'm waiting 300 Monte Carlo steps before I start to do this. And the frequency at which I actually do these events can be controlled from the main Python file. If you go here, when you call that steppable, you can actually set up the frequency, and I set up frequency to be every 100 Monte Carlo steps. So if I try to now run this simulation, okay, it crashed, so don't panic. So you can see that it can crash even with your instructor desktop. I'll just try to open the player again. Okay, and I have an invalid syntax somewhere. Oh, I have accidentally typed equal sign there on line 28. So let me go to line 28. Yes, accidentally add this. Okay, remove, save. Let me try to play it again. Okay, now it's working. Okay, I do start with a blob initializer. Okay, so let me just play the simulation. These are all the cells. Okay, and after step 300, you see that I start to create the links. The cells are going to start pulling one another on the left and the right. And because we calculate the links every 100 Monte Carlo steps, that allows me to actually re-implement those movements, and then I can have many rounds of cell pulling, and then this will lead to start to converge in one direction and extend in another direction. Okay, and I don't know. That's how implemented, and that's how the output is. Of course, you can change those parameters that I had before to make the simulation better. So yes, I can move the simulation so you can see the code. Okay, so that's basically the code, and I will upload this code to the student materials so you can actually do that. And the slides themselves, I do suggest making increasingly more advanced versions of this conversion extension module. Okay, and all of them will be of increasing realism. And all these other versions actually you have the implementation here. Okay, so I know that I little bit over time, and I will stop here. I'll make all this code available. I hope it makes sense and it illustrates how can you manipulate links from the Python level to do whatever you want to do for your own code. Okay, so here now I'm gonna just go back to slides. Okay, and I'll stop here in the last slide of this module, and please fill up the module experience questionnaire. If you need more help or have any questions, I can help to answer any question you may have while you wait for the next module. Okay, so thank you for your patience and attention. I hope that this has been useful for you.
Hi, Julio. Oops.
No, go ahead. Go ahead.
Thank you, Pedro. I was wondering, how do biologically cells do this? How do they determine their left and right and not their up and down and then pull?
Okay, that's a good question. So what must happen is that you must have a break of symmetry of the cells, right? So they can orient themselves in a certain direction, and they regulate their behaviors along this direction. Okay, that can be done by planar polarity. Okay, as you just said in the text. What causes planar polarity to happen can either be a self-organization or be driven by some kind of boundary interaction with another tissue, or some kind of morphogen gradient that exists. Okay, so there used to be some kind of molecular cue at the tissue level that breaks the symmetry of the cells. Okay, And once that breaks the internal symmetry of the cells become polarized, and then they start to pull each one. Well, they start to behave according to their polarization. I will cover how you can model planar cell polarization in the last module of the course. At the end of the afternoon, there's a way to do that using compartments and using a slightly different version of compartments by having dynamic compartments. Okay, but yeah, there's a upper level symmetry breaking event that polarize the cells in a certain direction, and then the cells start to change their. They have this polarized behavior, and that leads to conversion extension of the tissues or some other kind of morphogenetic movement.
Thanks.
Julio, have you
Yes.
ever implemented a kind of torque between links?
No.
Do you think it's possible to do?
I don't know.
For example,
Well,
if you want to build a snake,
okay. I see what you're saying.
a snake with one cell of width, like 100 cells of length and one cell with wide, I mean.
Okay. Let me just make a new share. Something like this. You make it make a big cell with links and have some kind of bending energy of those consecutive links.
Exactly.
Okay, so yeah, so that was done in 2007 by this group, right? That was before CompuCell. I think CompuCell was just beginning, so they did not use it. There is not a way to implement. I think MyCheck did a little bit of this, but I don't know if he really. I know that MyCheck was starting to implement this in CompuCell, okay, to kind of some kind of bending of consecutive links. One way that you can do that in CompuCell in a kind of hack manner is instead of having links between just this cell and this cell, you also add another link between this cell and this cell, two cells above, after it. Okay. Then you have, well, in this kind of, in the case we have three cells, then you have this link, and a link between this and this one. Okay. And by manipulating the target distance between this and also the strength, you can prevent those three cells to bend. Okay, so that would be an indirect way to do it.
Yes, I got it.
Okay, that's actually the way I do. I make epithelial cells to not bend too much, because if you only have links between this compartment, this compartment, just from the links itself, the cells can actually make a triangle, right? The compartments can make a triangle, even though you have links between the red and the green, and the green and the blue. Okay, but if you add a longer link between the blue and the red, then you straight up the cell.
Oh,
okay, it's an indirect
very
way to
clever.
do it, but you can also add some kind of bending energy that two consecutive links they should be the, another cost that penalize deviation
Yes.
from this direction to the next link direction. That's how we model filaments for the cytoskeleton. You add some kind of bending rigidity
Yes.
of
Yes.
segments of cell of filaments.
And do you know how they do this vesicle formation?
This one here.
Yes.
This was done. Well, that will be the next module. You add
Oh, okay.
links between the cell compartments and also links between the apical side of the cells. And in
Mhm.
this simulation, that is actually very old and I think was never published. Two things happen is that the link between the red cells, they decrease the target distance, or they become much stronger, so they are very compressed. So the cells want to that induce a kind of fur formation on those cells, like you see on this thing here. And the other thing that you was done is that you just increase the target area, the target volume of the blue compartment. Okay, and when you have those two processes going on together, you actually generate the not only the furrow and invagination, but actually the complete separation of this uh, tissue here from this tissue here. So I was not the one that did this, but I remember that that was what was going on. So if you guys have more questions about how links working uh, in CompuCell, feel free to ask. And the next module by Prion will be actually telling you how to manipulate links on with when you in the case where you have cell compartments. Okay. So we'll resume at noon. Okay, and then I'll be around if you guys have any more questions.
Sounds good. Thank you, Julia. It's like Julia said, we'll try to resume around noon if you'd like to take a quick break, grab a coffee. Maybe let's say 12:05, so people have enough time to use the restroom and grab a beverage.
Julio, I had a question. So in making models with apical constriction, so one way is what we'll be doing in the next module, but we've made models of the lateral line where instead of looking at it from the side where you see the polarized cells with compartments, you can do sort of a lateral view where you're looking at the primordium from the top. So you just are looking at the top surface. And so there we sort of go back and forth between whether using links is the better way to have apical constriction, which it actually doesn't do. It just creates aggregates of cells and clusters. So whether to combine the FPP links with changing the target perimeter of the cells so that they actually, because in actual apical constriction, it's the cross section of the apical surface that's becoming smaller. So we're trying to sort of combine the dynamics of the perimeter rather than the FPP length. What do you think about that?
Yeah,
as a way
that's
of
a
doing?
good. Yeah, that's a good problem because yes, in reality, what's happening is that the cytoskeleton, apical cytoskeleton is contracting and it's connected to the apical cytoskeleton of the other cells to um, additional junctions, right? So it makes sense to model that as a force. But as I say, if you just have the top view, if you just decrease the link, the one way that you can accommodate the decreased distance between two cells that doesn't change their area is by just having those cells kind of squeeze like this.
Yeah.
But if you have many cells doing this, you at some point you're trying to do, but you stop because the target area is just on the way. I think doing and again, just doing the target area, make the just the target area to shrink is another way that actually people have used to model invagination or apical constriction when being for the top. So I know
Yeah.
there are papers that model things like that.
Yeah.
Uh,
I
and
mean, one thing we had, I think is necessary is that if you just have all the cells shrinking, the tissue just becomes smaller. But if the shrinking cells, I mean, the cells with a smaller perimeter are attached in the periphery to cells that are stiffer, that create some, prevent the whole tissue from collapsing into just a smaller ball, then you start getting, we actually haven't done this exactly, but then you should get self-organization of constrictions within the field based on the tug and pull of cells on each other, and make sure that the adhesion between the individual cells is strong enough so that they don't just separate and become smaller.
yeah, so yeah, exactly. I totally agree with you what you said, and I'll try to model the thing by just decreasing cell area, but it's still good to have the links there because the links will prevent the cells from sleeping one another. This
Correct.
process, the cell should not change neighbors,
So
right?
that's exactly what I was thinking. So rather than have the links become the motive force for the contraction, you just help them to stabilize the organization, but
Yeah.
let the reducing perimeter be the driving force of the
Yes.
constriction, because that's actually what is happening in our system.
Yeah, and of course, what you can also do when you can have the links at the Python level, and you can make the target distance between links of two cells to be actually a function
Correct.
of the cell areas of those two cells.
Exactly. So that you have
And
R and then 2 pi R kind of a thing.
yeah, yes, and then the links will automatically adjust to whatever how much
Correct.
it can either be the target
Yeah.
of the area that you reduce or the current area. If it's a target, that actually will help the process a little bit to constrict. If it's only to with the current distance, you just make sure that's deviates. But I think having those model like that to be actually work very well because
Yeah, so that's what we haven't done that yet. Right now, we are still relying on the FPP links, but that tends to make like a cell knot or an aggregate rather than a
yes,
real beautiful constriction.
you
And
make a mix, right?
which is not exactly what's happening in our system, and it limits the number of cells that can come together also, because
Yeah, volume
it
exclusion. Yes.
yeah, exactly.
Yeah, I think that would be a better way to do it.
Yeah, that's what so we want to switch our model to that.
Yes.
Ajay, I will try to build an addition as I think it should be modeled in CompuCell,
Yeah,
creating extra pixels in the contact
yeah.
and to
So
pin the cell, right?
yeah, so I mean, the thing is, in the prime, what we are basically trying to do is in the primordium, you just have a rectangular field of cells, and
Mhm.
the whole thing is moving. And what we're trying to model is how many constrictions you get, because if the whole thing is relaxed, it comes together to form one giant constriction. But if it's moving, it pulls apart to make multiple constrictions. So the question is, what's the best way to model those constrictions to get that reorganization as dynamic as possible? So we've done it with the polarized apical basal lateral cells. That's one way of doing it. But the other way is to do it like you're just looking at the surface and use this combination of perimeter and